time. But. I can start. I think I've already been introduced. Okay.
Oh, thank you. You're here.
Okay, I'm sorry. No, you're not supposed to bring food in.
Yeah. I didn't see it.
Setting an example.
Yeah, I'm still being caught on
It's not
camera.
food, it's on.
It's on camera.
And you called yourself out.
Anyway, okay, so welcome to the afternoon session. I'm terribly sorry for the delay. First speaker is Dan Landsberg, and continue to tell us about. Right.
Okay, so let me remind you what we did this morning. We did some basic definitions of tensor rank and tensor border rank. I asserted but did not prove that they were valid measures of complexity. And we're talking, of course, mostly about matrix multiplication. And fortunately, we'll have lectures by Peter Bergieser to tell us the details about the upper bounds. I just alluded to you that there was a lot of progress. And I gave some discussion about lower bounds. And I told you there was some advances starting about 10, 15 years ago that have gone on for a while. And then they kind of were puttering out. And the reason was because of a barrier, but that's sort of only part of the reason. And I also finished the lecture by saying that we have a path now to potentially overcome these barriers by exploiting symmetry. So I should also say that all these advances that we made were obtained by exploiting symmetry and taking advantage of group actions. So because of that, I want to begin this lecture with another definition of rank and border rank that emphasizes symmetry and geometry. So let me give a new definition. Given S in some vector space A prime tensor B prime tensor C prime and T in some A tensor B tensor C. Well, these live in different spaces, but of course if A prime is greater than or equal to A, B prime is greater than or equal to B, C prime is greater than or equal to C, we could just view these as column vectors of height A prime and embed this space inside this space as the column vectors of height A. And this flexibility to allow ourselves to move tensors around will enable some definitions. We'll say S restricts to T if we can write T as some projection of S after possibly changing coordinates. So that is to say there's some matrix, some A prime by A prime matrix times some B prime by B prime matrix and some C prime by C prime matrix that projects these bigger spaces into the smaller spaces and perhaps changes coordinates such that this is in the image of this action of this group on this tensor S. My board handling space was bad. And we write S restricts to T. And similarly, S degenerates to T. And we write S like this. If we have T is in, now I look at the invertible matrices acting on S. But I take closure, so I allow limits. In particular, I can get any A by A matrix by taking a limit of invertible matrices. And yeah, so that's what I want to say. And now some notation. If I fix CR with standard basis, E1 up to ER, let me write M1 direct sum R is just the sum over standard basis vectors. But here, these three live in different spaces. So this would be the identity matrix if it was a matrix, or matrix with ones along the diagonal, R ones along the diagonal. And then, so this is often called unit tensor. And now the rank of T is less than or equal to R if and only if, oh, this is homework. Very fun homework, I might add. If and only if this unit tensor restricts to T, and the border rank of T is less than or equal to R, if and only if this unit tensor degenerates to T. And now we can see, like, if we want to think of things in terms of currency, this unit, we think of like this M1 copy, we think of this as having unit cost. So we think of the rank and the border rank of our tensor as two measures of the cost of our tensor. And with this language, we can also define value. And the Q of T is defined to be the largest row such that T restricts to the unit tensor of size rho, and Q bar of T, this is the subrank, and this is the border subrank. And this is the smallest row such that T degenerates to this. So this one will be larger, greater than or equal to this one. And I'm actually giving a whole course as part of this program on the cost and value of tensors. There are notes available if you missed the first week or so. But you don't have to worry because I'm starting a new topic on Wednesday anyway. So we just jump right in. It's a topic that's a mixture of something I know fairly well and something I'm terrified of. So you'll get both sides of the kind of lecture. So that's here. Only room 116, like just across the hall.
Is there a reason you don't allow projection in the definition of degeneration?
I do. If it's in the closure, it also includes projection.
Oh, it's A prime, sorry.
Yeah. I do.
Sorry, is this
Other questions? Yeah.
just a generalization of a diagonal matrix?
Yeah, it's exactly the generalization of a diagonal matrix. If I could draw a cube with ones along the diagonal and zeros elsewhere, that's what I would do, but I'm not very good at that. Other questions? Okay. So the reason I'm introducing this group, and since this group, let me just fix notation once and for all. this is the group we'll be talking about, so I'll just call it G instead of writing all this out. That we're seeing that we could define this rank and border rank in terms of the group action. And I want to describe invariance of a tensor. So now we have on the board 4 numerical invariants of a tensor, 4 integers we can associate to any tensor. But there are things more that have more information than just a number. And a very important one is the symmetry group. Of a tensor. So these are all the things. So I take a triple of invertible matrices such that this G, H, K acting on T does nothing. So these are the changes of coordinates in each of the 3 sets of variables that don't change the tensor. So for example, with this unit tensor, a little exercise, I think this is one of your homework problems, is if I rescale the first space by lambda 1 up to lambda r, and I rescale the second space by some mu 1 to mu r, if I rescale the third by 1 over lambda 1 mu 1, 1 over lambda r mu r, my coordinates will change, but this thing will not, because the changes cancel each other out. And we're here like G, H, K acting on a rank 1 tensor is just G acting on A, tensor H acting on B, tensor K acting on C. Now, you may ask yourself, well, how am I ever going to compute that? Well, actually, in math, we can't really, there's only one kind of thing I know how to compute in math. And so the only thing I know how to do is solve linear equations, right? So in math, when we have a problem that's difficult, we always linearize it. And instead of looking at symmetries, it will be more computationally effective to compute infinitesimal symmetries. So there's also the symmetry Lie algebra. So this is, like, I try to draw what passes for a German G. And let me call it X, Y, Z. And so these are in end A, which I sometimes like to write as GLA. But anyway, cross end B. So we don't require it to be invertible anymore. And now, but I have to tell you when I say x dot y dot z acting on t equals 0, I need to tell you what this action is. So x, y, z acting on A tensor B tensor C is x acting on A tensor B tensor C plus A tensor y acting on B tensor C plus A tensor B tensor Z acting on C. And why is that? Because if I have a curve G of t, H of t, K of t, that's the identity when t equals 0. I take the derivative at time 0. Of course, I'll have Leibniz rule. I'll get the derivative of this, and these two will be identity, et cetera. So that's why we have this funny Lie algebra action. And that is computable. It's a set of linear equations to compute the symmetry Lie algebra. And then from that, you can recover the connected component of the identity of the symmetry Lie group by exponentiation if you're not afraid of that. So that turns out to have a lot of good, useful information about the tensor. And I think people have studied these kind of things, at least in different contexts, for 100 years, at least. 150 years, I guess, for Lie algebras. And it has been useful to give us information about tensors. But now there's a more recent invariant. Yeah, so exercise, what is this thing if T is a random tensor? I should have put that. That's a good exercise. A more recent invariant is called the centroid of T. And this is kind of a strange thing. Again, this triple, now but now I require that x acting on the a factor of t equals y acting on the b factor of t equals z acting on the c factor of t. And again, this is a linear object, so it's computable.
Can you explain what is the notation?
Well, it's the same. Let me say it this way. Or if you like, yeah, I mean, it's the same notation as that.
It's the same action as in the Lie algebra.
Yeah, but it's just, this x acts on the a factor, y acts on the b factor, and z acts on the c factor. So now we allow x to move t, but we want to move y to move t in the exact same direction. Now, for most tensors, this thing is trivial. You don't get anything interesting. But so why? So I don't have time to explain where this comes from, but I do have time to explain what it's good for. And you'll have to take me on faith because our time together is limited. So why? So now let me go back to this, this handbook of algebraic complexity theory. One of the authors in the audience, the problem 15.2. So let's take a tensor T in Cm, tensor Cm, tensor Cm, and we'll say it's concise if this is my A, this is my B, if this is my C, if these three maps if all these maps are injective. And the informal way to say it is this tensor cannot fit into any smaller tensor space. That's all it means. So a matrix is concise if and only if it's full rank. But a tensor could be, tensor rank diverges from matrix rank. It could be much larger. And so, but it is true that if, I got ahead of myself. And we saw this morning T concise, that border rank of T is greater than or equal to M. And definition, T concise and from now on I'm going to deal with tensors in this space, is of minimal border rank if equality holds. And the reason this is important, you will hear about later this week. So I am relieved from the obligation of explaining it to you. But in a nutshell, these are the, as they say, these are the building blocks they actually use stone in the book. I wasn't sure if that was deliberate or not. Of fast matrix multiplication algorithms. So you'll hear about that later this week. And so they gave the problem of classifying tensors of minimal border rank. And this problem has become more important for proving upper bounds for the matrix multiplication tensor because the upper bounds sort of petered out. I mean, they still continued, but they did not continue very much in 1988. And around 2014, they started understanding why. So they were using one of these building stones named after Coppersmith and Vinograd, and they were getting all their, that was the best they could do. That was the tensor they got the best results with. And so you would rather have another tensor of minimal border rank that could give you better results. Now there's theorems, that's what I was about to say. 2014, they started having theorems explaining that the tensor they were using was not going to do any better, or not going to do much better than it already did. So there's that. It could do 2.38. It can absolutely not do better than 2.3. And so one would like to find another tensor that could do that. Any questions? Because I was a little vague.
Why is minimal border rank important?
Yes, I just said, I quoted their book, and they're the building stones of fast matrix multiplication algorithms. There's something called Strawson's laser method that is a black box as far as this talk is concerned, but will be revealed to you later this week, that eats one of these tensors of minimal border rank and spits out a matrix multiplication algorithm, or more precisely, a upper bound on the exponent of matrix multiplication. Strawson's laser method needs a tensor of either minimal or near minimal border rank. And I could explain why minimal, there's a tension between the two choices. And my time is very limited, so I'm cutting about 2/3 of my planned talk, which I think the audience will appreciate me not trying to give the full talk. So anyway, so just accept it on faith that this is an important problem. It was posed as an important problem in an important book. So why, I kind of changed subject on you. So theorem, Ilyashev, myself, and my student Arpan Pal proved that, well, sorry, that's not us. Sorry, that's a different theorem. This is the Buczynski family. Is that T minimal border rank, then the dimension of this centroid of T is at least M. So a random tensor will have trivial centroid. Here, the dimension has to be at least M. Yeah?
Does the centroid have more structure than that of a vector space?
Yes, oh, yes, thank you. And that's the theorem. That's the theorem I'm going to state now by those three people. Right. Theorem, the centroid is an abelian, a unital abelian algebra, and the three projections onto and A, NB, and NC. So T concise are injective. So it has more than a number. It has structure. And yeah, so now the point is when you have this additional structure, you can bring in tools to test. So if our tensor is of minimal border rank, it's a limit of rank R tensors. If our centroid of if our tensor is minimal border rank, its centroid must be the limit of centroids of unit tensors. So for those of you who know the language of algebraic geometry, we're in the world of deformation theory of algebras, and we have this kind of, I don't want to say the word trivial because it's non-zero, but we have this sort of very boring algebra, and our tensor is of minimal border rank if and only, well, a necessary condition for our tensor to be of minimal border rank is that one, our centroid has the correct dimension. That's just a number. But that's a necessary condition. But two, its centroid must deform to sort of a quasi-trivial centroid. So we can bring in the tools from deformation theory in algebraic geometry and commutative algebra. And the deformation theory is not subject to barriers. So
Just one question. Abelian algebra, this is associative algebra. It's not Lie algebra. That's
yes,
one
associative
usual subalgebra of.
subalgebra of endomorphisms. Yes. Not subject to barriers. So this object, it must have a certain dimension. Great. And that actually turns out to be better than any other equations for minimal border rank that we know of, any other isolated equations. But on top of that, we have this extra structure, this extra test that needs to be tested. And that extra test is not subject to any barriers. And so its cousins, which I won't have time to talk about for a higher degree, are not subject to those barriers. Other questions?
The high-level plan is to use this to find good,
Yes. Yes.
concise.
Yeah.
to the
And
metaphor.
so same paper. So before the story, m less than or equal to 3 was done. M equal to 4 is Friedland. Check this classification problem. Check. And then we did m equals 5 in this paper. And this was the first time that you actually needed some kind of deformation theory to finish the argument. We had candidates. We were not sure if they were minimal border rank or not. And deformation theory told us whether they were not or not.
Would it back for the centroid? How do you?
So x, y, z times x prime, y prime, z prime is x, x prime, y, y prime, z, z prime. Thanks.
Who is the P in the JLP?
My student Arpan Pal, and he is now in Idaho.
Does it cross?
Well, I crossed it out because I was getting ahead of myself. I needed to state the Baczynski family theorem before I stated our theorem. So I'm all stressed out because I only am going to do a quarter of my planned lecture, and I'm trying to at least get that
a few
quarter
extra
done.
minutes since I was late, for sure.
Anyway, right. So, so what time should I end, Nikhil? By that clock, not real time, that clock.
205 maybe? 207?
Okay. You tell me when to end, I'll end.
Sure, let's say 207.
Okay.
Sorry, Jacob.
Yep.
Kill me later, but this for the space of all commuting matrices, right? Like if you want to classify them for n equals 6 is already an infinite number of them, right? So what is your expectation when you say classify the tensors?
No. No. I did not pose this problem. This problem was posed in a book. And what I'm going to tell you shortly is it's a very difficult problem. You're getting ahead of me. And I'm going to tell you, you're anticipating what I'm about to say. Okay, but before I say those things, I guess I should say some open questions. And find example of T with dimension centroid T greater than 1 and less than m in an interesting way. I mean, you could always take the direct sum of something with a m-dimensional centroid and a zero-dimensional centroid and add them together. I want something interesting, not there's some obvious boring things. And then 1, 2, how large can the centroid of T be? So I'm telling you it can be at least m-dimensional. And when we first saw it, we thought maybe that was the maximum. And there's a reason for that, because it is the maximum under a very mild genericity hypothesis. But now we know there are actually concise tensors with rather large centroids. Right. So, okay, I think it would be criminal not to prove anything in a talk, so I have to prove something. So let me start the proof of that proposition, because I'll feel guilty the whole rest of the week if I don't. Right. So let's say I'm going to prove just part of the proposition. So say x, y. I want to show it's commutative. So then we have x prime acting on t. Well, that's the same thing as x acting on x prime of t, because it's just composition.
Are you going to prove something that you stated?
Yes, I'm going to prove
This one.
part of this. I'm not going to prove the whole thing, but I'll give you enough of the proof that you can fill in the rest by yourself.
Okay.
Because otherwise, how to get your foot in the door is the hardest part, as always, right? But this is the same thing as x acting on y prime acting on t. So remember, this is on the b factor, this is on the a factor. But now, this acts on the a factor, this acts on the b factor. From the definition, it's clear that the order doesn't matter. So this is the same thing as y prime b acting on x via a of t. But this, of course, by definition of centroid, is the same thing as x prime a x a t, which is x prime x acting on t. And so that proves that. And the rest is similar. Right. So I proved something. Good. I feel better.
Is the goal of classification to say, hey, look, these are all the possibilities and all of them are bad, so then there's a lower bound? Or something like that?
So actually, so let me tell you two theorems. So empirically, best tensor for this laser method, this is upper bounds on the exponent, is CWQ 1 and 2 theorem. So there's several people and then independently, Yelishev and some, I forget his co-authors, CWQ is the worst. I'm going to use a word that I won't define. One generic minimal border rank tensor for the laser method. Okay, so obviously these two sound very different. What the content of this theorem says is that I told you there's a barrier theorem for using this tensor in the laser method. And I'm saying no other one generic minimal border rank tensor has a barrier worse than this one. And we know explicit ones that have a milder barrier. So for this one, the barrier is 2.3. We have others that the barrier is something like 2.27 or 2.25. Okay. So there really is motivation. So the real thing they wanted was not the classification, but they wanted a better minimal border rank tensor for the laser method. And right. So,
And just to be clear, you want a fixed tensor for finite size M. You don't want an infinite sequence.
Correct. So for this CWQ, it's usually Q equals 6 or 8, depending on who's implementing the method. But let's not worry about that. Right. So now we can sort of right.
Go to 210 on that clock if you like.
What?
Go to 210 on the clock.
No. Look, I'm testing everyone's patience severely, so. Right, okay, so if I have 2 extra seconds, I'll say something to the experts in the audience. The tensors of minimal border rank. First of all, as Raphael was saying, classification is impossible, well, not impossible, but it reduces, even in a very special case, to a problem that's known to be extremely difficult in algebra and is considered intractable. So even if you had a more modest version of the question, there are basically theorems that say this is a wild problem and we cannot solve it. So then we want really the tensors that are subject to mild barriers. All minimal border rank tensors are subject to some kind of barrier, but we want one that's tougher than this one, right? We want an explicit one that's tougher than this one in theory and in practice. That's the goal. So what we want, if you think about it, are tensors that are closer to the unit tensor than this one. This one is as far away from the unit tensor as you can get. That's why it has the worst possible barriers among one generic tensors in minimal border rank. It's the furthest from the unit tensor. That is to say, every one generic minimal border rank tensor degenerates, in the language I used earlier, to this one. So this is the worst. So what we really want is the ones closer. Now, if we think about it, the tensors of minimal border rank is an orbit closure. And the open orbit is the unit tensor, and the unit tensor under change of coordinates. So what we really want to know are the components of the boundary and what the general elements in the boundary look like. And that is current work. by one of our postdocs here and others, is we found other components. So you take the unit, so a tensor, the set of tensors of minimal border rank is or at most minimal border rank, is the orbit closure of the unit tensor of length m.
Okay. Orbit closure of unit tensor.
Yes. And now I want to know what are the, so deep inside that is this one, and I want to know the things closer to the surface, closer to the unit tensor. That is the general elements of components of the boundary in the language of algebraic geometry. And now we found some, and what was remarkable is they have qualitatively different behavior from previously known. And we found actually 3 families of such. And one family I'm very, very excited about. And I will conclude by telling you what that family is and telling you my hope that it could lead to potentially lead to advance in matrix multiplication. So first I need to write down this CWQ, but I'm going to do it as a space of matrices, right? So we have this T from A star to B tensor C. So I'm going to tell you what T of A star is. This is a space of matrices of dimension M. So CQ, this sits inside C2Q plus 2. I didn't make up the notation, tensor to the 3. And it looks like this. A0, so the indices are going to go funny. A0, then A1, and let's let Q be even. A1 up to AP, AP plus 1 to A2P, and then A2P plus 1 all by itself in this corner, lonely little thing. Then AP plus 1, A2P, A1, AP, and zeros everywhere else, okay? So that is the world champion so far. It looks like that. It occurs in every dimension. I only wrote it in even dimensions because the thing I'm going to generalize it to appears in odd, in even dimensions as well. And now the theorem is let P, well, first of all, let P equal 7. It's to be precise. And F, a symmetric tensor. And let me emphasize any symmetric tensor. Then get a new tensor of minimal border rank better than CW. In theory. And I can draw it for you. So note this happens to be exactly P by P. And I just put in here F111 A1 dot 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 Fn11 A. Oh no, F11 J, AJ summing over J, Fn1J summing over AJ, F1NJ, AJ dot 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 NJ summing over J, AJ. So I could fill in anything coming from a symmetric tensor in this box, and this is still minimal border rank. This is also true, P equals 5. It's not true for P greater than 7, and P equals 6. I don't understand why it's not true, but evidently it's not. Or at least we don't have a proof that it's true in p equals 6. So there's some weird thing going on here. And now, you see, as you'll learn about Strawson's laser method, your C tensor of minimal border rank has a cost and a value. And by choosing minimal border rank, you're choosing something of minimal cost. But what you want is also maximal value, or as close to maximal as before. And the point is that here we have a guarantee, a certificate that this tensor is minimal cost. But we could put a tensor as expensive as we want in here and still apply the laser method. So the new thing is we only need to worry about value. We don't care about cost anymore in these special dimensions. And especially for those of you who know something about the laser method, this is a real opportunity. You just have to find an explicit cubic to glue in here that has tau value greater than 9.36, and you will prove the exponent is lower than 2.37. And I think that would be news. Thank you for your attention.
Thanks a lot, Dan. Any questions, comments? Yes.
When you prove these are of minimal border rank, do you give a sequence of rank decompositions? Is that how it
No,
works?
no, no. The proof is indirect. So we actually have two. Yeah, you actually kind of have to do something. You have to show some zero-dimensional scheme is in the smoothable component of the Hilbert scheme. So it's high tech.
Okay.
That it's minimal border rank, and that's why it's so weird to me that 5 and 7 are okay and 6 is not. But the deformation theory doesn't push through in that dimension. I mean, you expect for greater than 7 for it to fail by dimension count. So it's a subtle proof that uses machinery. Yeah.
So what does this mean? Get new tensor of minimal border rank better than CW in what you mean?
I'll tell you
Better?
precisely.
Better.
The asymptotic subrank of this tensor is strictly larger than the asymptotic subrank of the Coppersmith-Vinograd tensor. Therefore, the barrier it is subject to is not as severe as the barrier Coppersmith-Vinograd is subject to.
You say in this, so what you have thrown in red, the square one can put anything in, or I have to
Anything symmetric,
anything symmetric?
yes. Anything symmetric in
I'm
its
not sure
three
I-
indices.
I mean, this it is not a tuplets-like thing. I mean, because it starts first row A0, A1, AP, blah blah blah. But then I could not figure out the pattern in this row. It's not typo, really. It's not.
Yeah, I go from
A0.
1 to 2p, and then I swap order.
You swap order.
And I swap order deliberately so I could glue this in. If I didn't swap order, of course, if I didn't swap order, I would still get Coppersmith-Vinograd tensor.
Okay.
But I write the Coppersmith-Vinograd tensor in this peculiar way, which an expert like yourself noticed,
Okay. It's
only to give me the right to glue in this red blob. But it's still, a change of basis will send it to your standard Coppersmith-Vinograd tensor, don't you worry.
So given a red blob like this thing, how hard is it to crank the machine and compute the exponent it gives?
Right, so that you would need to ask Josh Ullman and Virgie Vasilevska-Williams because they're the world experts on it. And I know how to crank it in a most naive fashion, circa, the original stuff, but they're far more sophisticated than me, and we're working together. This is work in progress. So those numbers I cited are due to Ullman and Vasilevska-Williams. They actually computed the tau value that would be needed. See, so there's this, I defined one notion of value that is kind of theoretical, but in practice there's something Schoenhager defined, which we'll hear about later this week, called tau value. That's the actual practical thing. And that I don't know how to compute, but...
But in particular, it's not a mechanical thing. You need to apply.
No, it's art. If it was science, it would be done because we would have been working day and night to get it done. But it's kind of, you need to be a little creative because you have to make some choices and some partitions. And yeah,
great, maybe.
Okay, yeah. So maybe let's take a 10-minute break and meet here again. Thanks. Sorry to be late.